People think word meaning in models lives in lists or tables, so space feels irrelevant. Picture a three-dimensional cloud of points suspended around a set of axes, some already gathering into faint clusters. Each point is a word vector, an arrow from the origin to a coordinate that the model can compare. When the real mechanism kicks in, those arrows slide, rotate, and settle so that similar ideas pull inward while unrelated ideas drift outward and neighborhoods sharpen. Start with a scatter of arrows pointing in all directions from the origin, random and indifferent to meaning. As training begins, faint glowing paths connect words that occur together, like thin threads stretching between arrows across the space. Those connections are not decorations. They are forces that come from a comparison the model makes between the directions of arrows. Each update is a small shove along the surface of this space. Points with strong connections nudge closer in direction, while points with no reason to connect are pushed aside. The naive picture says the model stores definitions and then files similar words next to each other, like folders on a grid. That picture fails because the model never reads definitions. It only sees which arrows should line up to make accurate predictions of nearby words. So the right visual is not a filing cabinet. It is a field of arrows where co-occurrence draws lines, and those lines act like soft springs. With each pass, springs shorten for the words that match in context, and the arrows tilt to reduce their angles, forming pockets where clusters cohere. Look closely at a pair of arrows in this three-dimensional scene with an angle arc drawn between them. The key quantity is how much the arrows point in the same direction, not just how far apart the tips sit. When alignment increases, the angle arc shrinks, and the projection of one arrow onto the other grows. In practice, models often care about this alignment score, so the transformation you see is many tiny rotations around the origin that reduce angles inside a cluster and increase angles across unrelated clusters. Now add a translucent plane slicing through the space, its normal set by a chosen query arrow. On one side of the plane, the model says the word should be predicted as a likely neighbor. On the other side, unlikely. The gradient that changes the vectors is perpendicular to this plane, so each update pushes points across it in the direction that improves the score. Words that appear together get pushed toward the same side of many such planes, stacking up into regions, while words that do not belong move to the opposite side, leaving gaps between clusters. Do not mistake the cluster for a category label stamped ahead of time. There's no tag floating over a region that says animals or numbers. There's only geometry produced by the pressure of predictions. If you lay a curved surface over the cloud, think of it not as a fixed basin, but as the living landscape shaped by iterative steps. Points slide along contours, settle in valleys where alignment is consistent with many neighbors, and remain high on ridges when no context pins them down. Take a concrete example in this scene. Arrows for cat, dog, and puppy begin scattered, but as paths from shared contexts like fur, pet, and bark glow, those arrows swing into a tight wedge. In a different region, run, sprint, and jog tilt toward each other because the surface of motion context tilts their way. Draw parallel translation arrows between the animal cluster and a region containing lion or tiger, and you see a rough directional consistency, a vector offset that travels across the space. That offset is not magic arithmetic. It is the result of many planes and many alignments pushing parallel relations into nearly parallel directions. Mechanically, the model improves by pulling positive pairs together and pushing sampled negatives apart. In our three-dimensional picture, positive pairs draw green strands, and the arrows slide a little closer in alignment with each strand. Negatives mark red dashed paths, and those arrows rotate away to reduce the wrong alignments. Over many steps, the tug of green and the push of red carve the cloud into a set of clusters separated by clear gaps, with thin bridges where ambiguity forces compromise. Remember that the true space has many dimensions, far more than the axes we can draw here. When we project to 3 dimensions, we rotate a high-dimensional cloud and drop a shadow onto a 3-dimensional grid. A rotating set of axes helps you see this. As we spin the view, some clusters stretch or compress, and some gaps look larger or smaller. That distortion is honest. The neighborhoods we care about usually survive the projection, but fine boundaries can bend. Keep the mental note that what you see is a faithful analogy of directions and neighborhoods, not the whole geometry. Ambiguity shows up as points that refuse to sit deep inside a single cluster. Put a word like bank near both a finance cloud and a river cloud, with thin strands pulling in 2 directions. The arrow hovers between, and the path it takes during training oscillates along a ridge between those regions. In classic word vectors, a single arrow must average those forces, so it ends up in the middle. If you let the scene hint at contextual vectors, they would split into multiple nearby points, each falling into a different neighborhood determined by the local context. Zoom into a single arrow and draw its path through space as a faint trail. At the start, the trail is a zigzag of adjustments, short segments turning around different planes associated with different contexts. Over time, the trail smooths and shortens, and the arrow finds a steady direction that sits near its neighbors. The concept to keep is that learning is not a teleport. It is a path in latent space, a chain of rotations and small translations guided by forces that depend on what co-occurs and what does not. It is tempting to stare at distances from the origin and read meaning into length, but most of the structure lives in direction. Draw a unit sphere around the origin and project each arrow onto that surface. The main neighborhood pattern stays. High-frequency words often hover near the center or spread with short length, so normalizing to the sphere removes distractions about scale. On the sphere, clusters become patches on the surface, and the angles between arrows govern who is close and who is not. Now use the geometry for retrieval. Plant a new query arrow for an idea, and drop a perpendicular from each candidate arrow to the direction of the query. Neighbors are the ones whose projections are long and whose angle arcs are small. You can watch the nearest points light up in a tight region, not because we read a dictionary, but because this cluster was shaped by shared evidence in the training. For analogies, add a translation arrow representing a relation and look near its tip for arrows with small angle error. The scene shows that relations emerge as consistent displacements because the same planes push the same way across different regions. Do not overread the crisp edges in the picture. If you slide a plane through a dense area, there's always a gradient from the core out to the boundary, not a wall. Thin connections between clusters matter. They act like bridges that let information generalize between related ideas. Draw a mesh of light edges across the whole cloud, and you see that clusters are not islands. They are neighborhoods inside a continuous surface of directions. The model exploits those bridges when it maps new words or rare words by aligning them along shared paths. The most important shift is this. Meaning here is not a label. It is a location and a direction produced by many simple comparisons. The arrows and planes are not metaphors stacked on top. They are the mechanism. When you picture the forces that align and repel across a space, you stop asking where the understanding comes from and start watching how the cloud reorients until neighborhoods carry the statistics of language. Keep the final picture tight. A rotating cloud of arrows sits around the origin. A few regions glow brighter as clusters, and translucent planes tilt through them. Training is the repeated action of those planes, pushing arrows so that similar ideas share a direction and unrelated ideas face apart. When you think about word vectors, think about angles closing inside clusters, gaps opening between them, and translations traveling along straight paths through the cloud. That is the mechanism worth remembering.